Hello, physics students, and welcome to this review screencast by yours truly, Mr. Welch. I had some students ask me to do a review screencast before our test on Thursday. So this screencast is actually just going to cover energy. There's already a screencast posted on Work and Power, so if you want to review that stuff, you can go back and watch that screencast. But this one's going to deal with energy. So the first slide I have here is just kind of our tree of types of energy, okay? So just our general one, we'll just say energy. And our definition for energy, remember, is the ability for an object to do work. And in this unit, we talk primarily about mechanical energy and types of mechanical energy. And there were two types of mechanical energy. We had potential and kinetic. And there are actually two types of potential energy, and those were elastic potential and gravitational potential. So really we can say there were three types of mechanical energy, if we're trying to be really specific, but in general we would say that there's two types, and that is potential and kinetic energy. So here's our three types, our three specific types of mechanical energy. We have elastic potential, which is the stored energy an elastic object has due to its deformation or due to some deformation. And our equation for elastic potential was P ES is equal to 1/2 kx squared. Now remember, this k value is our spring constant, and it can never be negative, and this x value is actually the deformation distance, or the change in length of that elastic object. Okay, so oftentimes in these types of problems with elastic potential, I'll give you the relaxed length of the elastic object, and I'll give you the stretched length. So this change in x is the difference between that stretched length and the relaxed length. The next type of potential energy that we had, or the next type of mechanical energy that we have, is gravitational potential energy. And this is the energy an object, the stored energy an object has due to its relative position from a reference point. And the main thing to note with gravitational potential is that it can be positive or negative, because it really depends on where our reference point is. And I've talked a lot about that. That gravitational potential is just a relative value, but it's in reference to that reference point that we designate. And again, in most problems, I will give you the reference point, or if I don't give you it, you just assume that it's the surface of the earth, or it's the ground. Okay? And now the last type of mechanical energy that we have is kinetic energy. And our equation for kinetic energy is 1/2 mass times velocity squared. Now, this is our only type of mechanical energy that actually has a velocity in it. And this makes sense because kinetic energy is the energy an object has due to its motion. And for something to have motion, it needs velocity. Okay, so kinetic energy is the energy of motion, and we define it mathematically as Ke is equal to 1/2 mv squared. Now the next thing we got into was the conservation of energy, where we actually looked at how the energy of a system before and after is equal to each other. Main thing from the definition of conservation of energy was that the energy in the system has to remain constant. Okay, energy can either be created or destroyed, so it's a constant value. But we should note that energy can be converted or transformed. Okay, converted or transformed, and also transferred. Okay, it can be transferred from one object to another. And we saw that in the double ball bounce activity, that the kinetic energy from the basketball was actually transferred to the tennis ball. Okay, so energy in a system, the value has to be constant, but it can be transformed into different types of energy, and it can be transferred from one object to another. And we had a mathematical definition, of course, for conservation of energy, where we said that the total mechanical energy before an event was equal to the total mechanical energy after an event. And we can extend this equation out, and we can just list all the different types of mechanical energy that we have. So we can say, we could say elastic potential plus gravitational potential plus kinetic, okay, before is equal to the elastic potential plus the gravitational potential plus the kinetic after. Okay, so again, it's really important when you're doing problems that deal with the conservation of energy to start with this king equation right here. And then you can identify what types of energy are actually there before and after an event. Because a lot of these, oftentimes they cancel out, okay? So, you know, if we're just standing on top of a cliff, what does that object have? It has gravitational potential, so we don't even worry about kinetic or elastic. So this equation, while it looks big and scary, can actually get simplified down, and it's very helpful for us in that form. So here's just a sample problem. I did do a screencast on how to solve conservation of energy problems, but here's just another sample problem for you that you can go over, and I'll actually go through the process here. So we have a skier goes down a frictionless hill of 100 meters, then ascends another hill of 90 meters, and our job is to find the speed of the skier at the top of the second hill. So just a picture, if we start out with a picture, we have, let's see, there's our first hill and here's our second hill, okay? So this original height here is 100 meters, and this height of the second hill is 90 meters. So we could say that this 100 meters is our initial height and this 90 meters is our final height. So if we write out our big long equation where we have, you know, all of our types of energy, okay, so this is before, and then we have all of this stuff after as well. We can look at what actual energies we have before and after this skier starts to ski. Okay, so what do we have initially? Well, all we have, we know that they're at rest on the top of this first hill, so we can get rid of elastic, okay, see ya. We can get rid of kinetic because they're not moving, so all we have left on this left side is gravitational potential. Now what about on the right side? What about after over here? Well, we're back at a height, we're back at this 90 meters, and we know we have to find a speed because this skier is going to be moving now. So the only one that we can get rid of on this right side is elastic potential energy. So our final equation that we're going to use for this problem looks like this. Okay? Let me slide down a little bit here. So working with this equation, we can write this out and we can say that MGH initial is equal to MGH final plus 1/2 MV final squared. Now, I know a lot of you saw this in the homework problems and it kind of threw you for a loop, but all of these masses can just cancel out, okay? Because if we factor out the masses from this side and we divide by that mass, all these masses then just cancel out. So simplifying this equation down, what this is going to look like is GH initial is equal to GH final plus 1/2 VF squared. So now we can just simplify this equation down and get V by itself. Okay, so we'll have VF squared is equal to GH initial minus GH final, and this is all going to be multiplied by 2. Now I'm not going to do all the plugging and chugging here, but if we simplify this down one step further, we get V final is equal to the square root of 2 times GH initial minus GH final. Okay, and if we plug in our known values, the values that we knew from the problem, we get an answer that the final velocity on the top of the second hill is 14 meters per second. Okay, so that is our answer for this sample problem. The last thing that we looked at in this unit was the work energy theorem. And what we said in the work energy theorem is that the net work done on an object is equal to that object's change in kinetic energy. So for there to be work done on an object, there has to be a change in energy of that object. And we can extend this out even further, and we can rewrite this, and we can say KE final minus KE initial, which is just the same thing as our change in KE. And we could even take it a step further and say that the net work is equal to 1/2 mv final squared minus 1/2 mv initial squared. But if you know this equation, you should know how to go from here, from here to here, because basically we're just plugging in our known equation for kinetic energy at that point. Okay, so here's another sample problem with work energy theorem. We did one in class the other day, but I just want to be sure that we know the process that needs to be taken for this type of problem. So first off, let's list our knowns. We're given a mass here of 2,500 kilograms. We're also given a a final velocity, because we're told that this car starts from rest. Okay, so our final velocity is the 1.8 meters per second, and our initial velocity is 0 meters per second. And we're also given a distance of 20 meters. So our first job is to find how much work was done on the car. So using our work energy theorem, work net is equal to a change in KE. We can say that 1/2 mv squared, or mv final squared, minus mv initial squared. And we know from our given information that this velocity is 0, our initial velocity is 0, so this guy can go away. So then we can say that that our work net is equal to 1/2 mv squared. And if we plug in our known information, okay, our mass here and our velocity, we get a work done. We get a work done of 4,050 joules. Okay, so our work net on the car is 4,050 joules. Now, what was the magnitude of the force exerted by the mechanic? Well, now we take our other definition of work. Okay, now we say that work net is equal to a force parallel times a distance. Well, now we know our work net. We just calculated that. We're given a distance, so we can just rearrange this equation and say that force parallel is equal to the work net divided by the distance. So if we plug in our known values here, our work net was 4,050 joules. Our distance was 20 meters. So therefore, we get that the force exerted was 202.5 newtons. And that is our answer for this sample problem. So there was a quick run through of all the stuff that we talked about in this energy section of this work, energy, and power unit. As I said earlier, there's already been a screencast done on work and power. So if you want to review that, I'd go back to that screencast. And I hope this answered any other questions, and I hope this really helps you study for the test. Take care, physics students.